So today in our video lecture, we will tackle the last topic of the course in automatic control, which is a frequency response technique. So it will be specifically concentrated on only one method, which is Bode plot, right? So frequency response technique is a specific technique that you use to analyze a system when it is excited with a specific input, which is a sine wave input. So let's go ahead, look into the content and the outcomes of this chapter that I hope you will be able to achieve at the end of this video lecture. So frequency response analysis, why is it important? So that's the first part. Why is it important and where do we use it? So the purpose of it is, the first and foremost is basically is to identify two things, to identify amplitude changes, or what we call generally in automatic control as gain, and the lag, or generally called as phase shift. So it's to identify two things, gain and phase shift of a system when it is excited by a sinusoidal input, right? So there's a major characteristic where of a system where you need to use frequency response is when the system is excited by a sinusoidal input. So if you look into previous examples of system that we have studied, they were most of the time excited by a step input, right? But not all systems are excited by step input. There might be systems that are excited by a sinusoidal input. It means an oscillating force. So for example, here we can see a test signal, which is an input to a system. So this test signal is a sinusoidal input. It may be a force, an oscillating force, right? Or it may be an oscillating displacement that have been subjected to a system, right? And what we want to look at the output, what we want to look at is two things. The first thing is gain. So what is gain? Gain is the amplitude change. So we can see here one of the signal, the small one is basically is the test signal, is the input, and the larger signal and shifted over here is basically is the output signal. So there's two things on a sinusoidal input that we can identify. The first one is basically the amplitude change. So this is what we call gain. And the second one is the phase shift. So this is what we call phase shift, which correspond to the lag. For example, if you put an input, the response doesn't come until a few times later. So there's a lag. This lag is what we call phase shift. And it is identified in degrees. So a sinusoidal is, you know, that a complete sine wave achieve a complete period at 2 pi, so it's an angle. So a phase shift can be quantified in angle as well, right? In radian or in degrees. So why is this important to identify amplitude change and phase shift when it is subjected to sinusoidal input? This basically will help a designer of a control system, which you will become probably, to identify potential resonance, right? To identify potential resonance. So probably the amplitude change will become too important that will break the system. So is to identify potential resonance that can disrupt the system, or the bandwidth where the system reduce the response. So basically here we can see that the gain is positive, but it might as well be that the gain will be negative. So it means it attenuate, or it makes the output signal smaller. So we do, so there is basically a range of frequency of input. So this is a input signal, it has a certain frequency, and this frequency of course can change. There are frequencies where you have a certain amplitude change and phase shift. With another frequency you will have a different output, right? So there are frequencies, or what we call bandwidth, where the system reduce the response, where you wouldn't have any response anymore. So it is important to identify those. And it is also to identify, for another thing that we didn't write over here, is basically what we call instability. How do we find instability in a sine wave case? In a sine wave case, an instability would correspond to a phase shift of 180 degrees, right? So a phase shift of 180 degrees. So what does it mean? Let me draw quickly a phase shift of 180 degrees. So imagine if you have, so we will be plotting the signal at on the same axis. So imagine if you have here your input, right? If I change to another color for the output, let's say we have green signal for the output. If you have, for example, a signal that is, so instability is when you have a phase change of 180 degrees. What does it mean to have a phase change of 180 degrees? It is when your signals, your output signals is shifted by 180 degrees. 180 degrees means, so a complete sine wave is 360 degrees, right? 180 degrees means it is a phase shift of half wave. It means your wave only start over here, the output. So this is the output. So what does it mean? It means that if you look over here, if we are at a certain time t, if you put an input, for example, here at positive something, let's say I put a positive 1, the output that you will get is basically is at negative 1. It is exactly the other way around. You want the system to move towards one direction, but the system in response will move in opposite direction. So you give, for example, you give a displacement to a system to goes to the left, but it goes directly to the opposite direction, which is to the right. So that is instability. So for a system, for a sine wave input, system with sine wave input, we define the instability as going exactly in opposite direction, having a phase change of 180 degrees. So with frequency response analysis, so this is basically frequency response analysis, you will be able to identify these things. If there is too much of amplitude changes, if it attenuate or reduce the signal until you cannot see any output, or it phase shift until 180 degrees. So there are tools to identify this, because we're not going to plot every time for a single frequency, plot this kind of graph, a time response. Imagine we want to basically test for a different sine wave, for a different amplitude of, for a different frequency of sine wave, what would be the output? For example, for a range of frequency of, let's say, 0 Hz until 1 kilohertz, you are not going to plot 1000 from 1 to 1 kilohertz. You're not going to plot 1000 time response, right? So there is a method which is Bode plot. So now in frequency response analysis, there are several characteristics that we have to know that allow us to do this Bode plot. The first thing is that in the steady state, sinusoidal inputs to a linear system generate sinusoidal response of the same frequency. What does it mean? If you give an input of sine wave, let's say with a frequency of 50 Hz, the output, so here is the input, the smaller wave, the bigger wave here is the output. The output will have the same frequency. It will also be 50 Hz. If the input is 50 Hz, the output will also be 50 Hz. The only thing that could change are only two, which is the lag and the gain, the phase shift and the gain. Another characteristic is basically the frequency are the same, but the output differs in amplitude and phase angle. So the difference are function of frequency. The difference of phase shift and amplitude, they are a function of frequency. It means as the frequency of input changes, the phase shift and the amplitude will also change. So what is Bode plot? Bode plot is when you try to identify two things. So the two things that you want to identify is basically the magnitude. The magnitude means the gain, and the phase as the frequency changes, right? As the frequency changes. So how do we basically identify the magnitude and the phase? So how do we identify, therefore, the magnitude, or what we call the gain and the phase of the system as the sine wave changes in frequency? So what we do is basically we excite the system with input of sine wave that has a range of frequency that we are interested in, right? So the frequency input, we note it as omega, because usually it is a pulsation in radian per second. So it could be either in radian per second or in frequency, but usually in automatic control, in mechanical we use the frequency basically in terms of pulsation, which is omega in radian per second. So we change basically the input of the sine wave by its frequency from a minimum pulsation to a maximum pulsation, right? From minimum pulsation to maximum pulsation. So this will depend, of course, on the requirement of the test. So, for example, if you may be asking this for exercises in this class, the value of those omega will be given. But in real life, what will you do is you will test the system with different omega within the range that you're interested in. So, for example, from 0 hertz until 20 kilohertz for an audible excitation, or another signals. If it is mechanical, it goes from 0 hertz until 5 or 10 kilohertz, 5 kilohertz basically, because that is largely sufficient. But in our cases, it will be given, right? And then once you excite it with, for example, or at the first time you excite it with 0 hertz, and second time you excite it with 1 hertz, and then later you excite it with 10 hertz and 100 hertz, and each time you excite it, you will basically identify the magnitude and the phase. And at the end, what you're going to do is you plot the response of the system for each input pulsation on one plot. So that is Bode plot, right? So Bode plot. In our case, it's not going to be an experimental Bode plot. What I mean by experimental Bode plot is when you have a test bench, a test system, you give an excitation and you plot the response. You measure the gain, you measure the change of amplitude, and you measure the lag, and then you plot the graph. But now we're not going to do that. What we're going to do is a theoretical Bode plot when we plot it from a transfer function. So here, let's look at how do we do it step by step. So let's imagine you have this transfer function. So you have a transfer function of gs equals to, so it's 10,000 divided by s plus 5, s plus 20, s plus 50, right? So what you do first is basically what we're going to do is that we know that s is the Laplace variable that represent the basically the frequential part of the, because in Laplace we basically in frequential domain is represent the frequential portion, right? So what we do in Bode plot, in frequency analysis, what we do is basically we study the system as when s tends toward j omega, s tends toward a pure pulsation, right? So when s is purely pulsation, it means s equals to j omega. So what you do is basically you replace s with j omega. So let's do this together. You take a pen. So going to replace, what we do first is now gs will become j omega. We're gonna have a purely pulsation input. So here it's not s anymore, it's j omega plus 5 multiplied by j omega plus 20 multiplied by j omega plus 50. And then once you do that, what do you do? For the transfer function at a given pulsation omega, you have to find the two things. So omega will be given. So for example, let's say you have a range of omega will be given is omega in radian per second. You have to test for several omega. Let's say for 1, omega equals to 10, and omega equals to 100, and omega equals to 1000, 1 kilo radian per second. You have to test the system, right? So for each, so what happened is for that particular transfer function at this given omega, we will find two things. We will find the magnitude of the transfer function, because the magnitude basically will represent the gain, and you will find another one which is the phase. because the phase will represent the lag of the system of the response. So magnitude, what is the magnitude of the transfer function? So this has been seen in root locus, basically when we did a revision on complex representation of vectors, right? Representation of complex numbers. So the length, the magnitude represents basically, so if we have a transfer function gs, the magnitude of gs is basically the length of that vector, the length of that vector, the length of that complex vector. And what about the phase? The phase is basically is the angle of that vector. And once you find what happened is basically you will find the gain, the magnitude and the angle of each term. So here, how many terms do we have? We have one term over here. This is the second term. This is the third term, and this is the fourth term. We have one term on numerator and three terms on denominator. So we will have to find the magnitude and the phase for all of them, and then at the end, once you find the phase and magnitude for all of them, you have to for each term, you find basically first for each term, and then what you need to do is to sum up to find at the end the magnitude and phase for the whole transfer function gs, right? So how to do that? So let's take a look at an example. We'll do for one, for example, s plus 5. So now it's not s plus 5 anymore, it's j omega plus 5. So what we do is we have to replace it with one pulsation. Let's say we take the first one, omega equals to 1. So this term will now becomes omega equals to 1. It means we have j plus 5. And in complex vector, what does this represent? It represents a vector in this direction where the complex component is 1, it's just j, and the real component is 5, right? So in this vector, you need to find two things. You need to find the magnitude and you need to find the angle. So what is the magnitude? The magnitude is easy. You just use the Pythagoras theorem. So it is 5 square plus 1 square, square root everything. And what about the angle? The angle is basically, it's this angle. You can find it by arctangent. So because the tangent of this angle is basically 1 over 5. So it's the arctangent of 1 over 5. So now you have the magnitude and the angle of this first term, j omega plus 5. And you'll have to do the same thing for 1000, have to do the same thing for j omega plus 20, same thing for j omega plus 50. And at the end, what do? You have basically 4 vectors, and you have to sum up their magnitude and their angles. So here is a quick revision on the product of vector and division of vector. So basically, if you have like here s plus 5 multiplied by s plus 5, s plus 20 multiplied by s plus 50, a product of vector. So here is in polar writing, you have the magnitude over here. This is an example. If you have the magnitude of 35 and have an angle of 65 degree, multiply by another vector that has a magnitude. So this is a magnitude, this is an angle. So let's say this is magnitude 1, angle 1 for vector 1. This is magnitude 2, angle 2 for vector 2. The product of these two vector 1 and 2, basically it is the product of the magnitude, 35 multiplied by 10 becomes 350. And as for the angle, is the sum of the angle. So magnitude, basically you have to do the product. As for the angle, you have to do the sum of the angle. So the sum is 65 plus minus 12, it becomes 65 minus 12, 53. As for division, it's the same thing. If you have vector 1 and vector 2, vector 1 divided by vector 2, in terms of magnitude, you just divide. 35 divided by 10, you get 3.5. And in terms of angle, if it is division, then you deduct, right? So 65 minus 12, it becomes 65 plus 12, becomes 77 degrees. So these are the examples. But what you need to do now, I think you understand. Find two things. Find the magnitude and the angle for each terms, and then you sum them up. So at the end you get the magnitude and angle for your transfer function GS, right? So next we'll see how do we plot the Bode plot from there. So at the end in total, for this transfer function of GS equal to 10,000 divided by S plus 5, S plus 20, S plus 50, you'll get this kind of table. Right? You get this kind of table. So for the moment, we will only look at up to this part. So here on the left hand side, this is the table that you need to do. On the left hand side is basically the pulsation, is the frequency, right? So the frequency, basically the range that it is testing is from 0 up to 20 kilohertz, up to 20 kilo radian per second. So there are different values of omega that they are testing, and basically what happened is that now you have the terms here in the table. So the j omega plus 5, here you have j omega plus 20, here you have j omega plus 50, and here you have the numerator 10,000. And for each term, what you need to do is to find two things, the magnitude and the angle. How do you find magnitude? Again, so the magnitude is using the Pythagoras theorem. And how do you find the angle? The angle is basically the arctangent of the complex component divided by the real component, right? So if I have to summarize over here, if I have to write down a bit, so for each omega, for each value of omega, at each term you have to find two things, magnitude and angle. And the magnitude, what is the magnitude? Magnitude is basically using Pythagorean theorem. So it's a square plus b square square root, with a and b is the component of the complex vector. So let's say this is your vector, right? And you will have, this is the j component, and here you have a, here you have b. So this is the magnitude, calculation of magnitude. And as for the angle is basically its arctangent. So it is the inverse tangent of b divided by a. So the terms here, this is the vector that represents the terms, basically a plus jb, right? And our b is, of course, it's our omega, right? Our b is the omega. So just be careful when you try to find out the angle, because the angle is basically over here. If you have basically your a, here what we have is, what is the value of a's? The a's are all positive, 5, 20, 50. So they are all over here. So the vectors will be right like this, right? And no matter how much do you add in terms of omega, the vector will just keep going up and up, but it will stay in this quarter and not goes into other quarters. But if you have a, for example, the vectors can go to the other side as well. So when you identify the angle, please be careful with the direction of the vector, right? Another remark is, of course, we have a as positive in all terms, because why? If we have a negative, it means we will have a positive poles, right? And a positive poles would mean that our system is unstable and it is not even worth it to study. But of course, here it's all, the a are all positive, means our poles are all negative, right? So you have to do that for each term. Find magnitude and angle. Here magnitude, angle, same goes for magnitude, angle. And then for the overall transfer function, you sum up the magnitude and you sum up the angle, right? Sum up the magnitude and sum up the angle. But we're not done yet, because in terms of Bode plot is not plotted just in terms of magnitude and angle, but the plot is basically in order to make it obvious, to make the importance characteristic appears clearly, it need to be plotted in decibels. So you can see that the magnitude is not just the magnitude, it is basically multiplied by 20 log m. 20 log m is basically is the unit in decibels, because in decibel what happen is you can take a larger range of values. you can squeeze them in a smaller scale of a graph, right? 20 log m. And angle, of course, it stays as angle, but in terms of Bode plot, they will be also plotted in a logarithmic scale, so that you can have a larger range. Because if we look at here, it's 0, 0 0.1, 0 0.3, 1, and then you can go up to 20 kilo radian per second. So in order to be able to visualize everything, the scale will need to be decibel versus logarithmic, right? So these two parameters will be plotted as a function of omega. They are the magnitude in decibel and the angle of phase shift in degrees or in radian per second. So let's see a sample of Bode plot. So here is basically the Bode plot of the transfer function of GS. So the magnitude here, again, the magnitude, what you need to do at the end of your calculation, you need to multiply the magnitude by 20 log m, because the magnitude is plotted in decibel, and for the phase it is plotted in radian or degree. So here is in radian per second, and both of them, so this graph represent the magnitude or the gain, what we call the gain, and here it is the plot of the phase or the lag, or we call the lag, right? And both of them are plotted versus what? It's of course versus the parameters that we were testing, which was the frequency or the pulsation, radian per second, right? So we plot both of them, the magnitude. So as the pulsation increase, so here is 1, so here is 10, here is 100, and here we have 1000, because it is a logarithmic scale. As the frequency increase, we plot the gain. So these are the values that you have calculated, and we plot the phase. The gain is in decibel, the phase here is in degrees. So here we have the final product, the final plot of Bode plot of this particular system, right? So please try out the examples in the slide in Kalam, and then on this slide as well, and then later we look at how is this Bode plot useful for us. Right? So here we have another example of Bode plot. So it was done basically using MATLAB, because MATLAB have a command of Bode plot. So this is a different transfer function. Right? It is a different transfer function. GS of S plus 1 over S multiplied by S plus 4 multiplied by S squared plus 2S plus 2. So what you do is basically you just replace S with J omega, and once you have replaced S with J omega for each term, you calculate two things. You calculate the magnitude of the vector, and you calculate the angle of the vector, right? Here is the magnitude and the angle as omega changes. So here the omega that we tested was the omega ranging from 0.2 up to 30 radian per second. So different value were given, and then we basically find the magnitude in decibel of the system, right, and the angle, and then later we plot it in a Bode plot. So here on top is the plot of the gain of the magnitude, and at the bottom is the plot of theta of the angle, or what we call as phase shift. So what we can look at here is basically how do we describe this Bode plot. So the way to describe it is as the frequency of excitation increase, so in your system, as you increase the frequency of excitation, what does it mean is as your input gets higher and higher in frequency, your output will give different response. So as the frequency increase, the gain or the change in magnitude will drop. So you will have gains. What does gain mean is basically it's output over input, right? So at first it will be equals to 1, which means the output will be more or less equals to the input. But at the end, what happened is the gain it attenuates, what we call. It means that at the end, your output, as the frequency increase, your output decrease in terms of magnitude. So it decrease and decrease and decrease. But in terms of phase shift, at first what happened is you have it start with a phase shift of 90 degrees, of minus 90 degrees. So this is 90 degrees. Minus 90 degrees means that it has a certain lag, and as your frequency increase, the lag becomes more obvious and more obvious, and it will goes until minus 270 degrees. And then we see that it crossed the line of minus 180 degrees, as we mentioned in the early of this video lecture. If it goes to minus 180 degrees, we consider it as unstable, because you ask the system to go to the right, to one direction, but it goes exactly to the opposite direction, right? So that's how we read a Bode plot. So how is this useful in stability analysis? So in stability analysis of using Bode plot, what you need to identify is what we call phase margin. Because why do we want to identify phase margin? Let's have a look at what the definition of phase margin first of all. So what is phase margin? Here is we have a definition of it. So the phase margin is basically the difference between the phase at what we call phase margin frequency and 180 degrees. So how do we identify this phase margin frequency? So to identify this phase margin frequency, you have to look at first your gain plot. So on top you have your gain plot. At the bottom you have your phase plot, right, or lag plot. So when you look at your gain plot, you have to identify the moment when your gain plot cross 0 dB. Right? When it cross 0 dB. And okay, so 0 dB means if you look at the calculation of the gain, it's 20 log m equals to this plot. Log, which value of log will be equal to 0? Basically, it's log base 10 of 1, right? So a gain of 1 is this point. Gain of 1 means, what does it mean? It means your output divided by input is 1. So you have the output equals to your input in terms of magnitude. So it is basically what we try to look at is at this point, what is the phase shift? So when we plot right down to here, we can identify what is the phase shift at a gain of 1. So the phase margin, what is the phase margin? The phase margin is the difference of this phase shift and 180 degrees. It's the difference of this phase shift and 180 degrees. Why are we interested in this? Let's say if we have a phase shift of minus 90 degrees over here. Between minus 90 degrees and minus 180 degrees, we still have minus 90 degrees. So it means it shows you how far you are or how close you are to instability. So this phase margin basically it's quantify how far is your system at unity output, at unity gain, how far are you or how close are you to instability. That's what it means. So here we can see an example where we've on real concrete Bode plot, how do you identify this phase margin. So basically this is the point where we have that input equals to output. So again equals to 0, again in dB equals to 0. You plot down, you take a straight line down to the phase plot, right? And then the difference between this phase and 180 degrees, so this is basically minus 180 degrees over here. It start at zeros. Zeros mean at the beginning you have no lag at all, but the lag or the phase shift start to becomes more and more as you increase in frequency. And here it is basically the lag that you have or the phase shift that you have when your input and your output are equals. At the beginning you have an output which is a bit higher, now it is equal. So here is the shift when you have a unity gain. So this is the difference between this phase and minus 180 degrees. This is what we call phase margin. There is another margin which is gain margin. Gain margin is the other way around, but identifying the phase margin is sufficient in order to study the analysis of to analyze the stability of your system. So what is gain margin? Gain margin, I'm sorry, is basically the other way around. You identify the point when you are at minus 180 degrees, you plot up into the gain, and you can see the difference between your current gain and the gain of zero or unity gain. This is what we call gain margin, right? This is what we call gain margin. It means that if you are at this level of gain, you are now in instability. If you are at this level of gain, you are in instability. So you have to avoid this gain, right? So how do we conclude this in terms of stability? The system is stable if your phase shift at 0 dB is smaller than phase shift at 180 degrees, right? So we can see here, for example, your gain plot at 0 dB, your phase shift is basically smaller than the phase shift of 180 degrees. Then it means that you are stable. You have a certain phase margin over here. If I have to draw it out, so you have basically over here at 0 dB, we can see there is a certain phase margin. So this is the margin. So if your phase at 0 dB is on the left hand side of 180 degrees, then it's okay, you are stable. But if, for example, your phase margin of 0 dB, when you plot it down, it's on the right hand side of 180 degrees. So now you are in unstable condition. So your system is unstable. But for most part, our system, for example, the system that we studied just now, where you have GS equals to 10,000, right, divided by S plus 5, S plus 10, and S plus 20, and S plus 50, we can see that the poles are all negative, so you will not be in this case. But in terms of, let's say, if you have a transfer function that shows you this kind of Bode plot, then you know that you are in unstable condition. So that's all about Bode plot. The things that I need to teach you in Bode plot, you need to be covered. And by now, I hope that you can try several exercises in the slides regarding the tracing or the plot of the Bode plot. Try to do it on your own. Please be careful when you try to find the angle, especially. But there's nothing difficult in it. It's just basically manipulation of calculation in identifying the gain, and the amplitude, the magnitude, and the angle of a vector, and then you just sum them up and then plot them in decibel and logarithmic scale of the Bode plot. So that's all. I hope that it will be helpful for you, and good luck for your final exam. Thank you very much.